Okay, so we will now take a look at something known as the cross product. Now, there are actually two types of vector multiplication. One is the dot product, which we are already familiar with, and the other is the cross product, which we will take a look at now. And unlike the dot product, the cross product is only defined in R3. So for the case of 3 dimensions, if we are dealing with vectors that are in 3 dimensions, then only then can we take the cross product, right? For the case of the dot product, we can consider vectors in n dimensions, but that is not the case for the cross product. So let's define the cross product. Let's say that we have two vectors, v and w. So we consider these two vectors, and these are in 3 dimensions. Both of these vectors are in 3 dimensions, right? So the vector v has the components v1, v2, v3. We can also express this as v1i plus v2j plus v3k. And another way of expressing the components of a vector is using this notation. We have v1, v2, v3, right? And let's say the vector w has the components w1, w2, w3. Right, so we have these two vectors in 3 dimensions. Now the cross product of these two vectors can be denoted like this. So we have v cross w. So this is the cross product of these two vectors, and this will be equal to the determinant of a 3 by 3 matrix, where in the first row we have I, j, and k. The second row will have the components of this vector v. We have v1, v2, v3, and then the third row will have the components of w. So we will have w1, w2, and w3, right? And we know how to evaluate a determinant like this. We can expand across any row or expand down any column. Let's consider the first row. So we will have I times v2 w3 minus v3 w2. Then we will have minus j times v1 w3 minus v3 w1 plus k times v1 w2 minus v2 w1, right? So this here, this is equal to v cross w, right? And as you can see, we have the components I, j, and k. So this just resembles a vector, right? The cross product of two 3-dimensional vectors also gives us a vector. So this is itself also a vector. As you can see, we have the components I, j, and k. So this is also a vector. And this vector v cross w, this is orthogonal to both the vectors v and w, right? This vector is orthogonal to both v as well as w. Now what does that mean? It means that if I consider, so if you remember, if I have two vectors a and b, if I have these two vectors, if a is orthogonal to b, then the dot product of these two vectors will be equal to 0, right? If a and b are orthogonal, then their dot product is equal to 0. Similarly, since this is orthogonal to both v and w, then the dot product of v cross w with v as well as the dot product of v cross w with w will be equal to 0, since this and this are orthogonal as well as this and this. And now if the vectors v and w, if both of these vectors are non-zero, if they are non-zero, then what does that mean? It means that v cross w, this is also perpendicular to v, right? And it is also perpendicular to w, right? Meaning they're at 90 degrees to each other. And this cross product, so we've mentioned that this cross product, the vector that we get when we consider the cross product of these two vectors, is orthogonal to v and w, but these are not the only two vectors that this is orthogonal to. So let's say we have on a 3-dimensional Cartesian coordinate system. So this is my x axis, y, and z axis. Let's say I have the vector v. This is the vector v, and I have the vector w here, right? Now, if we remember from previous classes, the linear combination of these two vectors, so the linear combination meaning if I have some constant a times v plus b times w, where b is also a constant, this is a linear combination of v and w, right? So the linear combination of v and w can generate a plane. So let's just consider, let's ignore this z-axis, let's just consider the x and y-axis. Let's say I have the vector v like this and another vector w like this from my origin, right? Now, if I consider the linear combination of these two vectors, it will actually generate a plane. So, for example, if I consider one particular linear combination, let's say I have 2v plus 1w, right? Then what does this give me? 2v will be something like this. This is 2v plus 1w. So I will have some point like this, right? So I will have a vector like this. So this vector, let's say this is the vector u. So this vector u from the origin is just equal to 2v plus 1w, which is just a linear combination of v and w, right? Similarly, I can consider any other vector, absolutely any other vector on this xy plane to also be a linear combination of v and w. So this entire xy plane is just generated by all the possible linear combinations of the vectors v and w. So this linear combination generates this entire plane, and in this case it is the xy plane, right? So similarly, if I go back to my three-dimensional Cartesian coordinate system over here, if I consider the linear combination of v and w, it will just generate a plane like this that extends infinitely far, right? We will just have an xy plane in this case, and since the vector v cross w is orthogonal to v and w, meaning that this vector is at 90 degrees to both of these vectors, considering that these are all non-zero vectors, then a vector in this direction, let's say this is v cross w, this will be orthogonal to v and w, right? But if this vector is v cross w in the z direction, then this is also orthogonal to this entire plane, And we know that this entire plane is generated by this linear combination of v and w. So any vector on this plane, if we consider any vector on this plane, it is also orthogonal to the cross product of v and w, right? So v cross w is also to all linear combinations of the vectors v and the vector w, right? So this vector is orthogonal to all linear combinations of v and w. So it is orthogonal to this entire plane that is generated by all the linear combinations of these two vectors. Now, if I multiply the cross product of these two vectors by some constant, let's say some scalar constant k, right? Then this, what is this doing? This is just scaling this vector by a factor of k, right? So this resulting vector after scaling will also be orthogonal to v and w, right? So this is also orthogonal to v and w, as well as the linear combination of v and w. It is also orthogonal to the vector that we get from all the linear combinations of v and w, right? And the dot product of this vector with v and w, or the linear combinations, will also be equal to 0, right? So let's take a look at an example. Let's say that we have two three-dimensional vectors v and w. Let's say we have the vectors v and another vector w. Let's say that the components of v is equal to 4i minus 1j plus 3k. And for W, we have minus I plus 2j plus 7k. So we have these two three-dimensional vectors, and I want to find the cross products of V and W. So I want to find V cross W as well as W cross V, right? So let's start off with this first. So we have V cross W. This will be equal to the following determinant, where we have I, j, k. And since we have V first, we will consider the components of V in the second row. So we'll have 4, minus 1, 3, and then we will have the components of W. So we will have minus 1, 2, and 7, right? So this is just going to be equal to I. If I expand across the first row, I will have I times minus 1 times 7. We have minus 7. Then we have minus 6 minus j times 4 times 7, which gives us 28, minus 1 times 3, which gives us plus 3. Then we have plus k times 8 minus 1, right? So this is just equal to minus 13i minus 31j plus 7k, right? So we get this vector, which is equal to V cross W, right? So now let's find W cross V. So similarly, we now have the following determinant, I, j, k, and in this case, we consider the components of W first for the second row, right? So we will now have minus 1, 2, 7 in the second row, and the third row will have the components of V. So we have 4, minus 1, 3, and if I expand across the first row again, I will have I times 6 plus 7 minus j times minus 3 minus 28 plus k times 1 minus 8. And this is equal to 13i plus 31j minus 7k. Right, and this is equal to W cross V. Right, and as you can see, if I compare the results of V cross W with W cross V, I can see that one vector is just the negative of the other, right? I can clearly see that V cross W is just equal to minus W cross V. So we can clearly see that the cross product of two vectors are actually not commutative, right? This relationship actually holds for any two vectors that are in 3 dimensions. The cross product is not commutative, right? Clearly, V cross W is not necessarily equal to W cross V. Now, what is the geometric significance of this vector and this vector? What is the difference between these two vectors? Right? We know that both of these vectors, both of these cross products will give us a vector that is orthogonal to W and V, as well as any vector that can be expressed as a linear combination of W and V, right? But how do I find the direction of these two vectors? So what we can do to find the direction of these two vectors is use something known as the right-hand rule. We can apply something known as the right-hand rule. Right, so let's consider two vectors. Again, let's consider the vectors V and W. Let's say that the vector V is in this direction. So this is the vector V, and the vector W is in this direction. And we can consider that there is some angle between these two vectors, some angle theta. Now, how can I find the direction of V cross W? What is this direction? So what we can do first is we can use our right hand and point our index finger in the direction of V first. Since we have V cross W, we consider V first. So our index finger is in the direction of V, and our middle finger is going to point in the direction of W, right? And after doing this, naturally, our thumb will extend in the direction of V cross W. So our thumb will be in this direction. And this gives us the direction of V cross W, right? So, and you can see this clearly from the following diagram. Here you can clearly see that we have the vector v, and our index finger is in this direction, our middle finger is in the direction of w, and our thumb is naturally extending upwards in the direction of v cross w, right? Similarly, if I have this vector to be v again and this vector to be w again, maybe we have some angle theta between them. If I now consider w cross v, then how do I find this vector or the direction of this vector? So in this case, since we have w first, our index finger will instead point along w, and the middle finger will instead point along the vector v. And if I do this with my right hand again, naturally my thumb will extend towards this direction. So this direction will be w cross v, right? And we know that the cross product of two vectors is anti-commutative, it is not commutative. So this is also just equal to minus v cross w, right? We've already shown that we can write it as minus v cross w, right? And you can see this from the following diagram, right? You can see this in this diagram. For the case of w cross v, our index is in the direction of w, and our middle finger is in the direction of v. And from this we can find the direction of w cross v using our thumb, which is now pointing downwards. And this is also equal to minus v cross w, right? So for the previous case, as you can see, in the upward direction, this is v cross w, and if I consider minus v cross w, this is just in the opposite direction to this, right? It is now downwards, as you can see over here.